Hey everyone, in this video we're going to talk about section 8.2b, which is about Taylor polynomials. So before watching this video, you should have already read pages 18 through 30 of your Goldstein text. This video we're going to go over the portions that you should have filled out as you were reading. We'll discuss those and then look at a couple of examples. So remember, the whole reason that we're doing all of this is that the linearization that we learned about last semester, where you build a tangent line and use that to approximate. Linearization is kind of a weak model for approximating a function, and that's because that linearization is only a good approximation around that tangent point. So Taylor polynomials are a way to make better models. So a Taylor polynomial is a polynomial function that we use in place of hard functions like cosine x, e to the x, or square root of x. Those aren't the only ones, those are just some specific examples. Taylor polynomials allow us to approximate functions that would otherwise be hard to estimate with accuracy. So for instance, like cosine x is difficult to estimate because we can only really use like specific radian input values where we get out nice values from the unit circle. So like plugging in pi over 3, well, that's great, we get something out nice. But if I plug in 4, well, 4 isn't necessarily a nice radian value that's going to give us something on the unit circle, so it's hard to approximate what cosine of 4 would be. Or e to the x, okay, well, we know that that base e is an irrational number, 2.718, on and on and on. Okay, if I want to do approximate e to the fourth, well, now I'm multiplying that irrational base 4 times, and so it's not easy to approximate what that would be. Or even square root of x, okay, square root of 4 is great to approximate, we know that's 2, but square root of 5, I know that's going to be somewhere in between 2 and 3, but it's hard to make that estimation. So Taylor polynomials allow us to estimate these functions better. Okay, we know that as we add more terms to a Taylor polynomial, we get a better approximation. So we get a larger polynomial. That means that it's going to extend out how well our approximation is. The difference between a Taylor polynomial and a Maclaurin polynomial depends on where they're centered. So a Taylor polynomial can be centered anywhere, but a Maclaurin polynomial is going to be centered exactly at 0. And then our notation for how we're going to be naming Taylor polynomials, so p sub n will be the name of the polynomial, and then n is the degree or the order. We'll talk about there's a slight difference within those, but usually it's the degree of that Taylor polynomial. So if the highest degree is 5, we'd have p sub 5. Okay, if our highest degree was 12, we'd have p sub 12. Okay, so like in our example, p sub 5, I can see here that my highest degree was 5. Okay, so we'd say that was a 5th degree Maclaurin polynomial. And this is going to be the Maclaurin polynomial for sine x. Okay, on the next page, there are 3 major characteristics of polynomial approximators. So in other words, these 3 features of Taylor polynomials are always going to be true. So first, we're always going to match the function being modeled perfectly at the center of that polynomial. So depending on where we're centered, whether we're centered with a Maclaurin polynomial at 0 or just a Taylor polynomial at 2, that center of that polynomial will always perfectly match whatever that function is, okay? And that's because if I'm thinking about, thinking about something like this, okay, and I have my Maclaurin polynomial or whatnot, I know that point is tangent, so it's going to perfectly match up. Now, we know that as we go to the left and to the right, our approximation gets worse, but that center, it's always great. Number 2, the quality of the approximation decreases as you move away from the center. So again, like I was saying, as I move to the left or move to the right, I see that it no longer matches my function perfectly. But we can increase the quality of the approximation by adding more terms. Great. Okay. We're going to look at a couple different ways that we can generate new Taylor polynomials from known ones, okay? And our text gives us 3 different ways. The first way is that we can differentiate or integrate a Taylor polynomial term by term, okay? So for instance, as an example, let's determine the Taylor polynomial for cosine x. So our text gave us what our polynomial for sine of x is. Okay, so we know that sine x as a Taylor polynomial is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and going on and on and on, right? So we eventually stop with some other term, which would be, well, we'll just stop there, okay? Notice here that we're talking about a Taylor polynomial, so this dot 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 that I have is actually going to be something that I don't necessarily want to have, because a polynomial we know has a finite number of terms. It's going to be a series that is going to have an infinite number of terms. So let's just stop there, okay? So that's our Taylor polynomial approximation for sine x. Well, from sine x, how can we get cosine x? You should be thinking along the lines of, well, in the past we've always derived it, and that's actually exactly what we're going to do. Okay, so I'm going to derive both sides of what this equation says. Okay, so if I do that, and actually I'll come down here. Okay, so deriving sine x gives me cosine x. Okay, and now let's derive each of these terms here. Okay, well, deriving x is going to give me 1. Okay, now when I derive this, let's think about what's going to happen. Well, I know that in the numerator I have my polynomial term. My denominator, even though it says 3 factorial, well, we know that 3 factorial is just a constant. Okay, so that doesn't actually derive, that's just a number. Okay, so this is going to become, well, deriving this. Let's see, deriving my numerator, I'm going to bring down my exponent, subtract 1 from the exponent, and then I still have my factorial in the denominator. Okay, same thing, we're going to do the same thing to x to the 5th over 5 factorial. Okay, bring down my exponent, subtract 1 from the exponent. And then same thing here. I'm going to bring down that exponent, subtract 1 from my exponent. Okay, so here is our approximator for cosine of x, and I think we can actually clean this up a little bit. Let's look at those factorials, okay? So thinking about what we know about a factorial basically says that we're going to take that number and we're going to multiply it by all of the previous integers. Okay, so for instance, 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, well, how does that help us? Why is that going to simplify? Well, let's look at what we had in the numerator. In the numerator, I had a factor of 3, and my denominator also has a factor of 3. Okay, so that's going to end up reducing down. Okay, same thing here. My numerator of that next term had a 5. Well, my denominator has a factor of 5, so that reduces. And I can say the same thing here with my 7th. So what this cosine becomes is I really end up with 1 minus x squared, and then what did we have left over? Well, I had 2 times 1, so isn't that just 2 factorial? Okay, my next term, I had a x to the 4th, okay, and in my denominator, I had a 4 times 3 times 2 times 1. Well, isn't that just 4 factorial? And then same thing next here, I have an x to the 6th over, looks like I have all of the terms needed for a 6 factorial. Okay, so our general term that we're going to have for cosine looks like we're going to have x to the 2n power, okay, because all of these exponents are even, divided by 2n factorial, because all of our factorial numbers are also even. Okay, so let's write this out a little bit nicer. So we're going to say that cosine x is approximately 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and then going on to whatever our last term ends up being, I see that we have a sign flipper because we are alternating in sign, and we have an x to the 2n over 2n quantity factorial. So we can use Taylor polynomials that we know to come up with other Taylor polynomials by, for instance, deriving them, okay? We also could have integrated. So if we integrate cosine x, I think we can end up getting where we would have gotten back to. We would have gotten sine x, okay? So you can derive Taylor polynomials. Okay, the next thing that we can do is we can substitute more complex expressions for x. So in our example, we're going to find the 8th degree Maclaurin polynomial for cosine x squared. Okay, so we just figure out what cosine x is, but to find cosine of x squared, I see that all I'm really doing is I'm replacing what that variable of cosine was with an x squared term. So to do that, what we're going to do is we are going to take x squared, and I'm going to plug them in for all of our x's in our in our Maclaurin polynomial. Okay, so I'm going to have 1 minus, I'll have x squared squared over 2 factorial. My next term, I'm going to have x squared raised to the 4th power over 4 factorial. And then I'll have x squared raised to the 6th power over 6 factorial. Now, one thing just to notice is you're probably thinking, okay, well, how many terms do we need to do? Well, we eventually want to end up with an 8th degree Maclaurin polynomial. So we are going to simplify this down just so we can see what all of those exponents end up being using properties of exponents. But I always say just do enough terms, maybe more than you're actually going to need, and then we can get rid of terms at the end if we need to. Okay, so going from here, I'm going to have 1 minus, well, x squared squared is going to be x to the 4th over 2 factorial. Okay, my next one is going to be x to the 8th over 4 factorial. Then my next one is x to the 12th over 6 factorial. Okay, so we wanted to end up with an 8th degree Maclaurin polynomial. Well, we accomplished that in this term here. So there's no need for this other term here because this would make us a 12th degree Maclaurin polynomial. So our Maclaurin polynomial for cosine of x squared is 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial. And there we go. Okay, so something just to note is that we can create these by making those substitutions, and then any terms that we need to drop because we want to have a certain degree, we will do that. Okay, let's go ahead and flip over our page. We're going to look at our third thing that we can do. So we can also manipulate Taylor polynomials algebraically, okay? And so the reason that we can do this is that this can help us build up to something that we want to evaluate. So in this example, we're going to evaluate the limit as x approaches 0 of sine x over x. Hopefully, looking at what this problem is asking us to do, you should be thinking, well, I actually already know the answer to this. And we do already know the answer to this, okay? The answer to this is 0. Nope, the answer to this is 1. Did I catch you? Okay, so the answer to this is 1. We've already talked about that 2 different ways, actually. We looked at the graph algebraically and accelerated last year. And then we also proved this using L'Hopital's rule a little bit earlier on the semester. We're going to look at another way that we can simplify this using Taylor polynomials, okay? So let's just focus in on the function. Say that we have f of x is equal to sine x over x. Okay, so let's build a Taylor polynomial using this, okay? First of all, we want this to be centered at 0 because that's what we're trying to find the limit for. So the good news for us is that we have a Taylor polynomial expansion for sine of x at 0, okay? So we know sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And again, we just want to get enough terms where we're going to see some sort of pattern. So I think we're good to go from there. Okay, if we wanted, we could add another x to the 9th over 9 factorial, but we want a decent number of terms. Okay, so right now we have the sine x of the sine x over x of our function. So how would we manipulate this to get sine x over x? Well, we're just going to divide by x, right? That's how we would get this term. And I know that if I divide this portion by this portion by x, I'm going to divide all of my other portions by x, okay? Whatever I do on the left side, I'm going to do on the right side. So let's do that and let's simplify. Okay, so that means that x over x is going to be 1. Okay, let's see what happens here. So I have x cubed over 3 factorial divided by x. Well, I know that that's just going to reduce down one of my x's, right? One of my x's is going to divide out. So I'm left with an x squared over 3 factorial. Here, I'm going to have an x to the 4th over 5 factorial. I'll have x to the 6th over 7 factorial. And for our last term, I will have a positive x to the 8th over 9 factorial. Okay, so that's what we have for sine x over x. Okay, now what we're going to do is we're going to take the limit as x approaches 0 of both sides. Okay, well, let's see what happens. Okay, and actually I'm going to write this out again. Okay, so as we take the limit of this, let's look at what happens with each term. So if I apply x approaches 0 to 1, well, I'm just left with 1. Okay, as I apply the limit here, well, I know that I would plug in 0. This term would end up being 0. Okay, applying my limit to my next term. Again, plugging in 0, I'm going to have a 0. Okay, plugging in 0 again, I will get 0. And you guessed it, plugging in 0 again, I will get 0. Okay, and it doesn't matter that we only went, we only had 1, 2, 3, 4, 5 terms. If we had kept going on, I think all of those other subsequent terms would have also evaluated to be 0. So at the end of this, we had that this limit was equal to 1. So again, we already knew that. This was just another way that we can determine that this limit is equal to 0. Pretty cool that this one fact has multiple different mathematical proofs for why this is true. Before this unit is over, we're actually going to look at one more proof of why this is true. So something to look forward to. All right, to wrap up our video, this section gives different general forms for Maclaurin polynomials for arbitrary degrees for the functions listed. Okay, so in this video, we have talked about sine, and we've talked about cosine, okay? I'm going to give you two other ones that I think we will prove a little bit later on, but another one is the Maclaurin polynomial expansion for 1 over 1 minus x, and then the other one is natural log of 1 minus x, okay? So these four general formulas need to be memorized, okay? I've mentioned before that we're going to have a memorization quiz, so that's something coming up. These are 4 of the 5 Maclaurin polynomials that you're going to have memorized. We're going to talk about the fifth one. The fifth one will be e to the x. We'll do that in our next section in 8.3. But this is going to need to be memorized. So I'm going to be looking to see that you have the first couple of terms memorized. I can't remember if it's 3 or 4, but you will also need to have the general form memorized as well, okay? And the reason why is I think this section really showed us why it's important to have some of those memorized, because we can manipulate. So for instance, like here, we came up with cosine x by deriving sine x, okay? You knew the derivative of sine x was cosine x, but this is something that you needed to have memorized in order to be able to derive each of those terms, okay? Or similarly in number 2, we knew we were going to be plugging in an x squared, but you had to have this portion memorized in order to plug in x squared into all of those terms. So having these forms memorized is going to be really important to be able to do other things with it later on, okay? So that's all I have for this video. Come with questions to our next class, and I will see you all later.